All right, here we are in day 11 content. So, unfortunately, I was running very low on class time the last time. In fact, I think I went over a few minutes. So this is where we were. We were talking about Fibonacci, and I talked about the ratios of the successive numbers. For instance, if you take 8.5 and divide that out, it's like 1.6. And so we talked about that. First we're below it, then we're above it, then we're below it, then we're above it, then we're below it. And we can kind of see if you've had some calculus where you used a squeeze theorem or a sandwichy theorem or something like that. You can see that on both sides of this we're limiting in. And so our limit of the ratios is approaching 1.618, which is the golden ratio. So that's where we left off, and I told you to go home and think about it and work on some of those ratios. So I was running out of time. Just to wrap up Fibonacci really quickly so that we can be done with his stuff. One of the things that we need to know is that he made it kind of almost a mission in his life to tried to move mathematics, especially since he was right there in Italy, right there in the Roman Empire. He wanted to move it to the Hindu-Arabic number system as much as he could and get rid of the Roman numerals. Because as you can imagine, trying to do bookkeeping with Roman numerals is probably not a lot of fun. So he was trying to get rid of that and make it more streamlined, easier to work with. So that was one of his goals. The other thing that he saw is he was working problems. He would work a problem, and he would get a negative solution. And that kind of caused a little bit of a problem for him because in general, at that point in time, we would have just thrown away a negative solution. He would have said, oh, that's just a useless solution, or it doesn't make any sense. Why bother with it? So what he was trying to do was instead make the math and the real world align. And so, for instance, nobody goes out and say to a little kid, hey, you have 0 toys, or you have -3 toys, or you have whatever. We always say, oh, you have 5 toys, or you have 2 trucks, or whatever. So he was, at one point we struggled with 0. At one point we struggled with irrational numbers. And so Fibonacci was trying to make negative numbers make sense, is what he was trying to do. So what he started doing was, because of his bookkeeping, he said, hey, in bookkeeping, whenever you have a negative, perhaps that can be a debt. Maybe you owe me something. Maybe it's -$5 to you because you're going to have to spend that money, and then it would be positive to me. So in the accounting end of things, that balance and check kind of thing makes sense. Or perhaps if we were gambling or something like that, perhaps it could be a loss. Or if your business wasn't doing very well, maybe you could be losing money. If somebody stole from your business, stole half of your merchandise, then you could be at a loss, right? So he was trying to make real world sense out of a number that perhaps doesn't necessarily always make sense for those negative numbers. So that's kind of what he was trying to do. And again, just kind of moving us towards variables the way that the Arabs have been moving us. So that was kind of the idea. Whenever we look at the overall scheme of things that's going on right now, we've got a lot of political stuff going on. We already talked about the sacking of Constantinople and how the Turks were attacking, and there was, we had the Crusades. We created an Orthodox church through all of this, and what we see is that about this time, the Roman Empire is really going down. And while they're going down, the Turkish Empire is going up. Okay, and in fact, it'll develop into something where the Turks are awarded land and different prizes, I guess, for being the victors in a war. And so we actually have something being developed that's the Ottoman Empire. So we see that coming up. This time wasn't good for Constantinople because, of course, it's being attacked and you have people of burning books and things like that, but also just buildings in general. There were a lot of ruins going on, so Constantinople is just, in general, in ruins. And because of that, the population goes down, right? People don't want to be in places that are being attacked all the time, and places where you may come home and your house has been burned or it's been knocked to the ground or whatever. So the population's just going down. So the scholars that are here decide, hey, maybe we'd be safer if we go somewhere else. So in general, the scholars are going to flee to Europe. And that's how we end up with a lot of the stuff that we end up with now, with the math going into Europe where we're used to having seen it. So you might see people going to Italy, you might see people going to Germany or France, things like that. In general, you're going to see these works being translated into Latin. And then at some point, we're going to have a wonderful invention. It's 1440 AD. Do you know what it was? Yeah, the printing press. I don't know why, but we all know 1440 is the printing press. Somebody must have really instilled that in us. Yeah, so in 1440 we get the printing press, and all of a sudden it becomes to where we can mass produce things, so to speak. So texts that were in Greek or Arabic, or even some form of, I can't think of what the word is right now. I don't want to say hieroglyphics. It's the other one, diamond, Egyptian, we'll say. Okay, things that are in those, they're going to get first translated into Latin, because that is the language of the scholars. And then they're going to get mass printed. Okay, so, and when we say mass printed, we don't mean the way that we're mass printing things today, right? Like your favorite novelist puts out a book, I don't know, Patterson or somebody, puts out a book and there's 1 million copies of it. They don't mean like that. They just mean, hey, look, we've got this copy of Euclid's Elements and it's been translated into Latin, and maybe we have 10 copies of it now, you know, instead of just having the one original source. We might have enough that, hey, we can have a copy in Rome and we can have a copy in Florence, and maybe somebody up in Spain has a copy, and that's because of the printing press. Yay, go printing press. Okay, so that's really helpful in preserving the texts of antiquity, anything that has survived. Maybe we don't have just one copy that's sitting in the library in Alexandria and then that gets burned, right? So, okay, we're in trouble now. So that becomes issues. So maybe some extra stuff can survive if we have the printing press. All right, what else do I have? So I talked just a little bit the other day about the competition that Frederick put together for Fibonacci, and what we're going to see as we move forward into the Renaissance is that these mathematical competitions kind of become a big deal. So why? It's almost like a joust for mathematicians. So on the one hand you have Fibonacci, on the other hand you have somebody we don't know his name, and they're both asked to solve the same problem. Whoever can do it and do it the fastest, or maybe it's the most unique solution, or maybe it's the most beautiful solution, or whatever we want to have in there, but as our criteria, but these are on the rise. and in fact will be the center of some of our competitions or some of our controversies as we go forth. So as we get to the cubic, we'll see, oh my goodness, so much drama, so much stuff going on. And why do we care if we're Fibonacci or somebody? Well, because when you win, you get fame, of course, for both you and the patron that you're working for. So yay, mathematician, but also for the person who's sponsoring you, right? So we get fame, and that's awesome. But at some point, this turns into, hey, if you win one of these competitions, maybe you get speaking engagements. Maybe we might want you to come up to Rome and give a talk, or maybe we might want you to be, excuse me, what we now in modern days would call a visiting scholar or a visiting professor. Hey, you're really smart. Why don't you come and teach our students for a while? We'd like to see what you can do. So maybe that's extra opportunities. Maybe that's extra money. Excuse me. I have to dig out my cough drop. Okay, opportunities and money, these things happen. Maybe it's some kind of prize that you win that nobody else has, those things. So if you're really, really important, maybe word of you spreads and people want to come and be your students. And that could help too. So that's kind of what's going on there. All right. We have one more problem from this particular time period that I want to cover, and then, yeah, we might cut today's lesson short because I'm going to work on a review for a test, so yay. This problem is the 3x plus 1 problem. That's what it's called. Okay, so there's a famous unsolved problem that we don't necessarily know a ton about. And what it says is, here's a conjecture. If you have, for every positive integer, x, there exists some n such that f, and here is a problem in math, I'm just going to say it, f, and we've got this superscript here, this exponent, n, so in this case what the n means is it's an iteration of our function. Unfortunately, a lot of times in mathematics we use the same notation over and over to mean different things. So some people you might see f squared or f cubed or something like that. Sometimes we have things up here like the little apostrophe might mean the derivative, right? F prime or something like that. So whenever I've got the fn up there, sometimes if it was a 2, you might think, oh, that's the second derivative or something like that. So in this case, what they mean is that n is an iteration. So I'm going to stick that over here to the side. N is the number of iterations, and I'll show you how that works in a second. Just to make a little caveat there, that is not a square or a cube or anything like that. Equals 1 if you got some lovely f of x that looks like this. X over 2 if x is even. 3x plus 1 if x is odd. Okay, so they're defining their function like that. It's a piecewise function. So x over 2, I don't know why my x looks so weird. X over 2 if x is even, or 3x plus 1 if x is odd. So the piecewise bit of that just means I'm going to get to pick which piece I'm going into depending on what x I'm sticking into my function. So for instance, I think your book uses 5 or 10. I don't remember which one it uses. Let's use, let's use a fun number. Let's use 13. 13's a not nice number. So what we're going to do is say if x equals 13, then we're going to have iterations as we put this in. So f sub 1, or f superscript 1 of 13 is going to be, okay, on the first iteration we put in the 13. Well, 13 is odd. That means I get to pick my second line here, right? So I'm going to say 13 times 3 is 39 plus 1 is a 40. So my first iteration is a 40, okay? Now, what the function up here, though, says, what the conjecture says is that, hey, there's going to be some iteration, some time that I do this, where whenever I do that iteration, I get a 1. So in other words, do it again. And keep on doing it again until you get a 1. That's what they're telling me to do. So the weirdness to the notation on this one is that this is F2 of 13. And sometimes people want to say, stick in the 40 there. And I see what you're after because you're saying, okay, this is the first iteration where X was 40. But that's not... That would be the first iteration for 40. We're actually working on the pathway for 13 here. So we keep on saying 13 here, even though it feels a little funny. But what we do is we put 40 into the function. So, okay, what about 40? Well, 40's even. So when I put 40 in as x, I get 40 over 2. So anytime I have an even function, I just divide it, or an even x, I just divide it by 2. So I get 20. Okay, well that's not a 1, so the function, the conjecture says do it again. So f of 3 of 13, I don't know how you would say that, f3 of 13. Okay, well 20 is also even, so to do it again, I get a 10. f4 of 13, stick in the 10. 10 is even, I get, divide by 2, that's a 5. And everything looks like we're going to be home free, except for now 5 is odd. So slow your roll just a little bit. On the 5th iteration here, I have to stick in a 5. So that's odd. 5 times 3 is 15. I put it in the second one right here. 5 times 3 is 15 plus 1. I get a 16. And it looked like all hope was lost because all of a sudden it got big again. But the really cool thing is 16 is actually a really nice number for me. I'm really happy we got 16 because as I do the 6th iteration of 13, I come up here and I put 16 in. Okay, we're back to being even. So that's going to be divide by 2. I get an 8. I do the 7th iteration, I stick the 8 in, it's even, so again I'm on the first line. I divide by 2, that's a 4. The 8th iteration, stick the 4 in, divide by 2, I get a 2. And on the 9th iteration, I stick the 2 in, I divide by 2, I get a 1. Okay, so what we would say here, and I'll give you the notation for this in a second, but what we would say is it takes 9 iterations. So my n that I'm looking for, basically, there exists some n. And the n in this case, whenever I put in a 13, was 9. So it takes 9 iterations for me to get down to this 1, which is what it said would happen. It says, hey, all roads lead to 1. That's what it's telling me. So sure enough, what we would call this is the pathway for 13. C of 13 is 9. Okay, and if you wanted to see the pathway, the actual pathway would be a 40, leads me to a 20, leads me to a 10, leads me to a 5, 16, 8, 4, 2, and 1. And sometimes I've seen people just list it kind of like a series. Like, hey, here are all my iterations, here are all my outcomes from sticking the remainder part back in and doing it again. Okay, so you'll see it written in different ways. I'm good with any of these. That one, this one, or even just listing it out as a sequence, I'm fine with that. Okay, so the deal is though, hey, how do you know How do you know that it's going to always come down to 1? And this one's actually one of those unsolved mysteries to speak of. There are similar problems that have been done with smaller numbers, not the 3x plus 1. And there are some solutions to some of those similar problems. And some of those similar problems actually involve Fibonacci type numbers, which is kind of cool. But for these, we don't quite know. There has not been, I don't think, a proof for why this works. Okay. However, I knew when I saw 16 that I was in good luck. Okay. And the reason for that is because 16 is a power of 2. So whenever I see that I've got a power of 2, 16 is 2 times 2 times 2 times 2, 4 of them. So whenever I see that I've got a power of 2, I go, oh, well, it's only divisible by 2, right? So I'm going to divide by 2, divide by 2, get 8, divide by 2, get 4, divide by 2, and eventually I'll get down to the 1. The one that was the problem child was actually the 10, because 10 is 2 times 5. And so whenever I look in that, it's not just powers of 2. So I know there's going to be this 5 guy that comes out eventually, and that 5 guy is going to be odd, and it's going to rocket me back up because I have to multiply by 3 and then add 1. So boom, I get bigger. So I'm getting smaller, I'm getting smaller, I'm getting smaller, I'm getting smaller. Oh no, that's an odd. Boom, it blows it up again. So, but there's something in this process of multiplying by 3 and adding 1 that eventually, if I had an odd number, eventually I'll stumble upon a power of 2. Okay, so that's kind of what's happening here. It doesn't have to be the 16. It would have worked just the same if I had seen a 64, because that's a power of 2. So as soon as I see, oh, one of my outcomes over here is a power of 2, okay, I'm on the right path. I'm doing well. So that's kind of the idea there. So I'd like to do one of these. Thought I had one written down. Dun, 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 dun. Let's try your book. I think your book had 6 on it. Let's do 18. 18 will be fun. So just as a reminder, here's our function. F of x is x over 2 if x is even, 3x plus 1 if x is odd. So let's do 18. Okay, so if you're watching at home, you can press pause and then come back and see us in a minute. We're going to go ahead and work it out. So think about it, see if your work matches up with ours. So when we put in the 18, we get an even number. So we go for this first guy, divide by 2, we get a 9. And then on the second iteration of the 18, I said x is 18. On the second iteration of the 18, well, 9 is odd, so I'm going to have to multiply. So that's 27 plus 1. That's a 28. Okay, which, again, you can see this ballooning effect. All of a sudden, we went from 9, whoa, way up to 28. Now, I'm looking at 28. It is not a power of 2, so I'm going to have to mess with it for a little bit. The F3 of 18. That was even, so I divide, 14, divide by 2. And the F4 of 18, well, 14 is also even, so I'm going to divide by 2. And then here's where we see, hey, 7. Now, the nice thing about 7 is it's just prime all by itself, right? But the problem is it is odd, so when I stick it in there, 3 times 7 is 21 plus 2. And because it's a weirdo, 7, a weird odd guy. It's not just a 5. Whenever I put it in there, I get out a 22, and that is not a power of 2 either. So when you have an idea, hey, I'm looking for the powers of 2, that helps me out. Unfortunately, when I divide by 2, that gives me an 11. F7 of 18, that's an odd number, so I'm going to multiply by 3. I'm going to get 33 plus 1, which is 34, which is still not a power of 2, but it's getting close. I'm kind of all around the powers of 2. F8 of 18, that's a 17. F9 of 18, oh no, I can't do that math in my head. 17 times 3, so that 21. Carry the thing, 51, is that 52? Check my math. I think it's 52. Okay. But that's okay because that gives me a 26. And then that gives me a 13. And hey, we know, oops, I don't need to do that. We know that 13 will get me where I want to go because we already did 13, right? So in 9 more steps, here is my path, right? So I know I can get there. So sometimes it becomes a matter of, oh, I'm kind of bouncing all over the place, but then all of a sudden maybe I see a number I've already seen before. Hey, we've already done 10. Hey, we've already done 5. Hey, we already did 13. So I can tell the rest of the path from there. So here's my path. I've got a 9, a 28, a 14, a 7, 22, an 11, a 34, a 17, 52, a 26, a 13. So I know that was 11 steps, but then I know from there I've got a 40, a 20, a 10, a 5, 16, 8, 4, 2, and 1. So it's kind of a longer path. But again, here was 11, so 12, 13, 14, 15, 16, 17, 18, 19, 20. It takes 20 iterations. So however you want to put that together, n equals 20, or you could say the path for 18 is 20. Okay, however you want to do that. But just to get across the point, hey, I had to put it into that original function up there. I had to keep on taking the whatever I got out, my output, and putting it back in and redoing this cycle over and over and over again. But it did lead to a 1. So that's the idea of the 3x plus 1 problem, is that eventually all roads will lead back to 1. So, and then you're done. Woohoo! All right. The follow-up on that, and I'm not going to play with this one too much, but I hope that gives you an idea about the 3x plus 1. If you're still looking, I think there are a couple of extra examples in the book, so hopefully you're reading that and looking into it. So there's this x plus 1 problem is the follow-up to that. And this is one of them, the problems that ties into the Fibonacci sequence. Okay, so it looks like this. A sub 1 is x, and for every n greater than 1, we have a sub n is equal to, again, it's a piecewise function, a sub n minus 1, but it's a recursive function because you can see I want a sub n, and I'm going to the guy before it, a sub n minus 1, over 2. If the guy before was even, or a sub n minus 1, plus 1, if the guy before was odd. Okay. And so what ends up happening is you get a very similar thing where everything converges down to 1. So for instance, if you used n equals 6, then your a sub 1, it says here, your a sub 1 is always whatever your x is. Oops. Did I say n? X equals 6. Oh, it is in. I'm sorry. My problem is right here. Those should all be n's. I'm like, why do I have 2 different variables running around? So all of these should be n's because that's the notation they've got. If we don't like that, if we wanted it to be in x's, we could make it a sub x plus 1, a sub x minus 1, that kind of thing. Okay, so all of these are in. So the first a sub 1 is just going to be whatever I have that I'm sticking in. So it's a 6. And then once I put that in, I'm going to come up here for the next guy. A sub 2 is going to be, go to the guy before it. That's your a sub n minus 1, because I was on the 2 guy. Now I'll look at the 1. Stick that in, 6 minus 2, or 6 divided by 2, that's a 3. So it looks very similar to what we already did, right? But instead of 3x plus 1, it's going to be the guy before it plus 1, the difference. So for instance, here, my output is an odd. So I'm going to use the odd line here. Circle these guys off. I'm going to use the odd guy here. So whenever I do that, I say, okay, so I'm going to put in the previous guy for my a sub 3, plus 1 is a 4. Well, my a sub 4 guy is going to be the guy before it was a 4, divide by 2. That's pretty easy, it's a 2. And then look, that's an even as well, so I'm almost out of space. A sub 5 is 2 divided by 1, or 2 divided by 2, which is a 1. So whenever I'm using this guy, 6 only has 5 iterations in it. And it's looking at the same kind of thing, but looking at it as if it was recursive. And because I'm doing that, you can see that I've got kind of that Fibonacci feel coming to it. And so they actually end up writing it, if you wanted to, they have this weird notation. If you want the next term, kn plus 1, then what you can do is find the last term and add it to the guy before it. So they end up doing kind of a Fibonacci thing. It's not quite the right notation for Fibonacci, because Fibonacci says take the 2 guys before, so they want n minus 1 and n minus 2. Instead, this is like if you want the next guy, look at your current guy plus the last guy. So that's what they end up using. So if you're not sure about that, take a look at it. I'm not going to stress out too much about it. I just think it's interesting that some weird rabbit problem from Fibonacci can end up being tied into some piecewise function that we're looking at. That's kind of interesting. And this one right here has a solution, the n plus 1 guy. And so because it has a solution, what they're basically doing is try to work a simpler problem than what the 3x plus 1 guy is. So somebody said, hey, if you look at this other problem that's similar, I can see this Fibonacci thing. And they're trying to use that to come up with a proof for why this guy always works. Why? That's what they want to know. So it's kind of one of those mysteries that's out there, and they want to know, but they're pretty sure that it can be tied back to Fibonacci somehow. Just hasn't quite been proven yet. Kind of cool. All right, so there we are. That gets us all the way through Fibonacci and a little bit more even. And as I'm looking at my notes, the next thing that I have in it is the cubic controversy, and I just don't want to start on that yet. I don't want to do that before we take our test. So I'm going to call that the end. So it's about 35 minutes worth of notes here. So when we come back after the test, we'll look at the cubic controversy. Ooh. And why we're uncertain who should get the credit for it. So that's where we're headed. In the meantime, what I'm going to do is I'm going to work on the review for test number 1, because we haven't had a test yet. So I'm going to work on the review, and I'll probably make a review video just to kind of give you formatting for the test and things like that. And then I'll post some notes online and things like that. So good luck on the test. Anytime next week you want to take it, that's a good thing. And if you have questions, let me know. All right, thanks.